Well, thank you for inviting me here. Certainly more fun to be here than Michigan right now. It's cold. So, okay. So the title is Motivated Cycles and Functoriality, and everything I'll speak about is joint work with Atsushi Ichino, who is right there. So the basic question that we've been interested in is the following. So we'd like to ask the following question: is Langland's functoriality? So is functoriality given by algebraic cycles? So first, in general, you can't expect something like this, but so you want to refine this question. So I'm going to sort of add something here. So at least functoriality for, say, cohomological automorphic forms. On Shimura varieties. Okay, so that's the question I'd like to discuss. Okay, so let's start by doing an example. So more or less the simplest example of functoriality comes from what is called the Shaky-Langland's correspondence. For GL2. So here's a simple example you can keep in mind. Let's say x1 is the curve x0 of PQ, where P and Q are two primes, not P not equal to Q. And let B be the quaternion algebra over Q with discriminant PQ. So this is the modular curve, but you can analogously look at curves coming from B cross. So these curves are denoted usually this way. Okay, so what this notation means is that you take this quaternion algebra, you take a maximal order, and then you take the norm 1 elements in this maximal order. And that also gives you a discrete subgroup of SL2R, and you can look at the associated curve. Okay, so both these curves are curves defined over Q. And what Shaky-Langland's plus Eichler-Shimura tells you is the following. If you take what it tells you is that all the modular forms, say, of weight 2 that you can find here also occur over here. Okay? And so you get some relation between Galois representations. So if I take H1 of X2 QL coefficients, and when I write this, I'll always mean the following, always mean H1 et al. Of X2 Q bar QL. So this notation is just shorthand for that. I don't want to write all this. So this is contained in H1 of X1 QL as Galois representations. So both of these are representations of the Galois group of Q bar over Q, and this one is contained inside there. So what this tells you then is that if you let J1 be the Jacobian of X1 and J2 be the Jacobian of X2, then this tells you that you get a map from, because H1 of the curve is identified with H1 of the Jacobian, so you get a map from H1 of J2 QL to H1 of J1 QL. And then we can apply Faulting's theorem, which is essentially the Tate conjecture in the setting. Faulting's tells you that this in fact comes from a surjective map from J2 to J1. Okay. So there is an actual geometric map underlying this. And a map at the level of Jacobians is the same thing as giving a correspondence in the product of curves. So equivalently, there exists a correspondence of, I'll say, delta inside the product curve x1 cross x2, which maps down by these two projections, P1 and P2, such that this map, this map over here, is obtained in the following way. You start with h1 of x2, QL. You pull back by P2. So you go to h1 of x1 cross x2 QL. Then you take the cup product with the class of delta. So this lands in h3 of x1 cross x2 QL1. And then you push forward by P1. P1. This goes back to x1 QL. Okay. So geometrically, you can think of this in two ways. You can think about this as a map at the level of Jacobians, or you can think about it as a correspondence on the product x1 cross x2. So if you're teaching an undergraduate class, a basic undergraduate class, at this point, a student might ask, can you give an example? And what they mean is, can you give a numerical example with numbers? So I'm prepared for that question. So here's an explicit, here's a really explicit example. Let's take x1 to be x0 of 26, and x2 to be x0 of 26, 1. Okay? So the second curve comes from the quaternion algebra of discriminant 26. All right. Then, in fact, you can, if you just look in the literature, there are equations. You can find equations for x1 and x2. And so here's okay, so that's x1, and this is x2. All right. So if you're bored in the rest of the talk, what you can do is take these equations and try to actually construct a correspondence on x1 cross x2, right? And let me know by the end if you're successful. But this sort of tells you what this theorem is telling you here. There really is a correspondence on the product of those two curves, which is, of course, very hard to find using the explicit equations. But that realizes Shaky-Langlands in this setting. Okay? But really what makes everything work is this theorem of faultings, the Tate conjecture in this setting. So what we're interested in really is the higher dimensional case. Okay. So just continuing, here's the second example. And we can stick with Shaky-Langlands, except we now take F to be a totally real field. And let's take B1 and B2 to be two quaternion algebras over F. And with the following property, we want them to be split at the same set of infinite primes. So B1 and B2 are split at the same set of infinite places. Okay. All right, and we'll assume that pi is a Hilbert modular form. We have parallel weight 2. That admits transfers to both B1 cross and B2 cross. Okay. Now, remember, we're assuming that these are split at the same set of infinite primes. So let's say that B1 and B2 are split at infinity 1 through infinity d, and then ramified at the remaining primes, so infinity d plus 1 through infinity n, where the degree of f over q is n. Then what you see is that B1 cross R is isomorphic to B2 cross R. And what you get is a product of copies of GL2 at those infinite places. So you get GL2 R to the D. And then you get the Hamilton quaternions to the N minus D. So the multiplicative group of quaternions. And you have associated Shimura varieties, which I'll call X1 and X2. And again, what the general theory is, so in this case, it's not just Shaky-Langlands, but Shaky-Langlands plus many other people, I guess Langlands, Brzezinski and Lebesgue, Carriol, Breimann, so forth. There are a whole lot of people who studied sort of the Galois representations that you get. A corollary to all of this work is that if you take the middle dimensional cohomology of X1, then and take the pi isotopic component, this is isomorphic to the same thing, but for all L. Okay? And so you're sort of in a similar picture, and what you would like to say is that what you'd like is for this isomorphism to be realized by an algebraic cycle. Okay? This is what. So the question is sort of, is this realized by an algebraic cycle? And so another way to say this, if you know what the Tate conjecture is i.e., can we verify the Tate conjecture in this setting? Okay. And of course, you can ask this problem in great generality. You can start with two Shimura varieties associated with different reductive groups, and you have two automorphic representations such that the pi1 and pi2 isotopic parts of the cohomology are isomorphic, at least at the level of L-adic cohomology, and you can ask, does it come from a cycle? Okay, so this turns out to be a very hard problem, right? It's very hard to produce algebraic cycles. So what I'd like to do is to say something just slightly weaker than this, and that's what we'll get to at the end of the talk. But let's first just discuss in what way you can sort of weaken the notion of an algebraic cycle. So right. So on the one hand, what you can do is you can take, if you have a variety X and you have an algebraic cycle, you can look at the cohomology class of this cycle in usual Betti cohomology, in usual singular cohomology, and that gives you a Hodge cycle. So all the way here, so if X is variety over K, it's a number field, and let's fix some embedding of K in C. Once you fix such an embedding, then you can, an algebraic cycle will give you a Hodge cycle. So let me give myself some space, actually. Okay, so I'll need some space, so I'll put that here. So a Hodge cycle is just something in, let's say we have cycles of codimension D. Then this is something in H2D of X, Q, that lives in the DD part for the Hodge federation. Okay? Okay, but, and the Hodge conjecture, of course, predicts that any Hodge cycle, right, in fact, comes from an algebraic cycle up to 10 string with Q. But there's sort of many intermediate notions, and so the one intermediate notion is to Deligne, the notion of absolute Hodge cycles. And but there are two sort of notions that sit in between here and here that I'd like to discuss. So here, there's a notion of what I would call Hodge-Tate cycles. So let me say roughly what this is. The point is that you see, if you start with an algebraic cycle, this part is just remembering its class and singular cohomology. But you could also remember not just its class and singular cohomology, but in all the L-adic cohomologies. And then you will get, and there are compatibilities between these because of the isomorphism theorems between Betti and et al. So the way you should think about this is these are basically Hodge cycles that are Galois invariant. Okay. So what I mean is you start with your Hodge cycle, which lives here, but think of it in H2D et al. Of XQL, right? And then it should be Galois invariant. And this notion of absolute Hodge cycle is even a bit stronger. The idea is you not just remember what happens in Betti and et al. Cohomology, but also Durham, algebraic Durham cohomology. Okay. So this is basically an rational algebraic Durham class. With the property that if you have an algebraic Durham class, then you can, because it's an algebraic Durham class, for any embedding of this, so you can think not just of your fixed embedding, but you can take any embedding of K and C, then what you can ask is, so for any such embedding, you will get associated Betti and et al. Classes, and what you'd want to say is that, so I'll just say these are rational algebraic Durham classes X, such that for all sigma X is a Hodge-Tate cycle. Okay. So Deligne introduced this notion, and basically the reason he introduced this notion is because the Hodge conjecture is sort of very hard to prove, right? And algebraic cycles are very hard to deal with, and this is sort of a linear algebraic substitute that is as good as possible. It sort of sees all the cohomological information and all the relations between them. But then it turns out that there is another notion here, which is even a bit better. This is the notion of motivated cycles. This is due to you, Andre. And Andre's idea is the following. If you start with a smooth projective variety and you take a hyperplane section, then so you have this you have the strong Lefschetz theorem, which says that so if let's say X has dimension D, you get such isomorphisms. And Andre's idea is the following. You start with, so the class of motivated cycles is obtained as follows. You start with the class of algebraic cycles. You allow yourself all the usual operations you can do in algebraic cycles, like pull back, push forward, intersection, whatnot. But then you also allow yourself to invert these strong Lefschetz isomorphisms, okay, for all possible for all possible such x's and l's. And so this is roughly sort of the idea that basically these are classes of algebraic cycles, or classes obtained from algebraic cycles by allowing all the usual operations plus inverting strong Lefschetz. Yes. What is it? Oh, slightly bigger. Okay, sorry, I will. Okay, from the next board onwards. Okay. And so the way to think about this is, this is really geometry, and if you go all the way there, it's just linear algebra, right, in a sense. And the closer you get to this side, you have more geometric information. Okay. And so this is really about as close as you can get to algebraic cycles without being right there. All right. So with this background, I'd like to explain the work that we've been doing in the past few years on functoriality and how it relates to algebraic cycles. Okay, so we have two papers. One of them is on the archive, so from June 2018. This is called, I think this is called Hodge classes. Oh, sorry, I should write bigger. Hodge classes. Is that big enough? Okay. Okay, so that's the first paper, and there's a second sort of paper in progress. And this is called, what you can imagine, motivated. Okay. So what I'd like to describe is sort of the results in these papers and sort of the techniques that we use, and then say something about what you might expect in the more general case. Okay. So first let me, so this is, I'll say paper A, and this is paper B. So this is the main theorem of paper A, is the following. So what it says is that in this setting of example 2, when you have these two quaternion algebras, right, B1 and B2, what it says is that in fact the Shaky-Langlands correspondence for pair B1 cross B2 cross is realized by a Hodge-Tate cycle. Okay. So in other words, we're not able to get there in this paper, but we're at least able to get here. Okay. So what we're doing is, okay, we can't produce this cycle, but we can produce a class, a Hodge class that is Galois invariant for all L. Okay. So a corollary to this theorem is the following. It says that a corollary is that you get an isomorphism of rational Hodge structures such that if you tensor this with QL, I call this I, this is Galois invariant. For all L. So previously, all that was known was that for every L you have this isomorphism of these Galois representations, but they were not tied together in any way. Okay? What this is saying is that there is an isomorphism of rational vector spaces that, moreover, when you tensor with C, preserves the Hodge filtration, and then when you tensor with QL, is in fact Galois invariant for every L. So they're all sort of tied together by this single isomorphism of Hodge structures. Pi isotopic component, yes. Correct. Okay, further. Yeah. Right, otherwise this wouldn't be true, of course. Okay, so that is what is proved in this paper, and I'll say a bit about the proof of this in a bit. But of course, the natural thing to ask then is, can you say something about like the Durham class? Can you prove something stronger, right? Can you actually? Okay, and this turns out to be a bit hard. To say something directly, to prove directly, for example, that it's absolutely Hodge. Okay. But now it turns out that we can do something much better. We can directly show that, in fact, it's represented by a motivated cycle. And so that is this other paper that we're writing now. So the main theorem of B is basically that, in fact, all right, but it's sort of even better than that in the sense that the motivated cycle is in fact fairly explicit. And this is what I want to get to. Like the general conjecture, of course, like the Tate conjecture predicts that you should have an algebraic cycle, but it's not just hard to produce algebraic cycles. There's no reason to expect you should be able to make any explicit algebraic cycles. In fact, I mean, the only way we know how to construct algebraic cycles on Shimura varieties is by using sub-Shimura varieties and so on. And if you have a product of these two Shimura varieties, there are no interesting sub-Shimura varieties. So you really can't expect to produce explicit algebraic cycles that realize the correspondence. But what we're saying is that the next best thing is true. You can actually make an explicit motivated cycle that realizes the correspondence. Okay? And I'll say more precisely how this is done. Okay. Well, it's more or less unique, right? Because if you take these analytic representations are irreducible. Many times irreducible. So if it's irreducible, then it's more or less unique. So, okay, any questions? All right, so what I want to explain sort of is the idea of the proofs. And of course, this paper builds on that one, so I'll start by explaining the ideas in A. So here's the idea of the proof. So what do we want to do? We have this product variety x1 cross x2, and we are trying to produce some kind of cohomology class on the product that realizes this correspondence. Okay. Right. So the first idea is you embed this or map this to another Shimura variety x. Right. So you embed this product in some bigger Shimura variety. And then you construct a class upstairs and then pull it down and then hope that it does the job. Okay? All right, so the first order of business is to find some larger Shimura variety which contains the product. Now, what we do is, it's nice to use unitary groups for this. So you pick a CM extension and you pick this in such a way that E embeds in both B1 and B2. Okay. All right. Then you can think of B1 and B2 as Hermitian spaces over E in a natural way. So we'll call B1, right, V1 for B1 and V2 for B2, thought of as E Hermitian spaces. And it turns out that so the groups B1 cross and B2 cross are very close to the unitary groups U V1 and U V2. So what you're led to consider is this product U V1 cross U V2. So I'll put a U E here, maybe just to. So just so very roughly, you can replace this Shimura variety by the Shimura variety associated to, by an analogous Shimura variety associated with that product. And of course, you have to work with GU and so on, but let's ignore things like that. All right. Now, this product sits inside the unitary group UEV, where V is V1 plus V2. Okay. Right. And then there is an associated Shimura variety there, and that is going to be, that's going to correspond to this X, larger X. All right. Now, what can we say about these groups? Remember that there's some set of infinite places where B1 and B2 are split, and then some set of infinite places where they're ramified. So at least over the real place, what does this look like? So if you take a real place and you take V in sigma, where sigma is the set of places where B1 and B2 are split, then this group looks like U11 cross U11. sitting inside U22 for V in sigma. And if V is not in sigma, then this looks like U20 cross U20 and U40. Okay. All right. So in any case, you get some associated Shimura variety, and we want to somehow construct a cohomology class upstairs. Now, how can you construct cohomology classes? You can do this by constructing automorphic forms that contribute to cohomology. So really, we want to construct some nice automorphic form, and there are not so many ways to construct automorphic forms. One way to do this is by theta lifting, and the idea is to use theta lifting. But of course, there are theta lifts between unitary groups, and it turns out that's not useful. What we need to do is to use some sort of exceptional isomorphism or exceptional isogeny. So the key fact here, we use the fact that U22 is essentially O42. This is not exactly true, but this is very close to being true. And the lifts that we want are going to come from SL2. Okay? And the whole thing is sort of motivated by Kudla-Milson theory. So in the 80s and early 90s, Kudla and Milson studied sort of locally symmetric spaces and cycles that you get from embedded locally symmetric spaces. And they have this theory of trying to understand what the Poincare duals of the cohomology classes of these embedded cycles are. And they showed in many cases that these are actually obtained as theta lifts. Okay? Now, in Kudla and Milson, they actually looked at cycles, and then they proved that these cycles, the corresponding cohomology classes, came from theta lifts. But in our case, it turns out there are no interesting cycles in the degrees that we want. Nevertheless, you can still write down these Kudla-Milson-Schwarz forms, and you can still write down the Kudla-Milson theta lift. Okay? So this is sort of the motivation. What we need is we need some inner form version of this isomorphism or this isogeny. And this involves the following construction. At some point, you have to do some arithmetic, right? And the idea is that you have this V, and you have B1 and B2. You let B be the product of B1 and B2 in the Brauer group of F. Okay? Right. And on the one hand, you have UE of V. That's this side. On the other hand, what we replace it on this side is by a quaternionic unitary group. And so this is roughly the same thing as UB of V tilde for some V tilde, which is a skew Hermitian B space of dimension 3. Okay? Very roughly, V tilde is constructed just by taking the wedge 2 of V. But then you have to show that it actually admits an action of B, and you have to construct a form and so forth, and all this is done in that paper. Read it there. Okay, so the basic idea, okay, let me erase this. Okay, so we started off with, so we have this UEV, but then we replace it by UBV tilde. Let me write this here. And you can think of X as being associated to this UBV tilde. And then you make a theta lift from UBW, where W is a one-dimensional Hermitian B space. Okay. And this group is essentially B cross. All right. So, and if you look at Kudla-Milson theory, what they will tell you is that if you want to construct the kind of thing we're looking for, which is analog of something that has 1-1 cohomology on O42, you should start with weight 3 forms on SL2. So weight 3 holomorphic discrete series on SL2. So the whole construction depends on some auxiliary choice. And the auxiliary choice will be actually depends on two auxiliary choices. So we'll pick a form G, which is a Hilbert modular form of weight 33333. Okay? So it's somewhat unusual. You have to use an auxiliary form of weight parallel weight 3. And you pick something that in fact transfers to GB, to B cross. And so what you have to put here is GB. And then you make a theta lift of this GB using some, not just Schwartz functions, but you have to use Schwartz forms at infinity because you want to get a differential form. Okay. And so this gives you some cohomology class. So I'll just call this theta phi of GB, and I'll call this psi 0. So by writing these Kudla-Milson classes, you actually can get a DD, this you can think of as a DD class on X. So the upshot of this construction is somehow by making this auxiliary choice and writing down some theta lift, you can actually make a cohomology class on this upstairs variety. Okay? All right. Now, there are two things that you need to do. The first thing you want to show is that when you restrict it to x1 cross x2, right, you want to show that in fact it gives you what you want. Namely, it could be 0 for all you know. Right? So you need to know some non-vanishing of periods. Right? So that's the first thing one needs to know. Non-vanishing of a period. The second thing one needs to know is the following. This process has just constructed a DD class, right? That by itself is not a Hodge class because, after all, a Hodge class is not something that's just DD, but it's a rational class that is of type DD. Okay? So the second thing is you want to show that in fact this psi 0 is a Hodge class, and it's not quite going to be a Hodge class, but it is a Hodge class up to scaling by some non-zero scalar. Okay? And the final thing one needs to understand is what the Galois action is. So you need to understand what the Galois action. So there's some associated automorphic representation, which I'll call big pi, and we need to understand the Galois action on H2D x, and then take the pi, big pi, as a component. Okay. So I want to say very briefly how these three things are accomplished, okay? And then we'll move on to the motivated cycles. All right. So for the non-vanishing of periods, there is some. We're looking at U11 cross U11 inside U22, and we're using the fact that U22 is essentially O42, and U11 cross U11 corresponds to O22 cross O2 inside here. Okay, so there's some symmetry that's broken, and the idea is that when you take this three-dimensional skew Hermitian B space, you want to break it up as a sum of a two-dimensional and a one-dimensional space. Okay, that's this sort of symmetry breaking, and so it turns out that you write your V tilde as the sum of V1 tilde and V2 tilde, where the dimensions are 2 plus 1 over B. And so you get a diagram as such. And now you're in this, you get a seesaw pair in the sense of Kudla. And what you're interested in is in computing some period on this side, and you can transfer it to a period on this side. Okay? And the period on this side becomes a triple product period. And turns out the other auxiliary choice you need is, so this UB of V2 tilde is essentially E cross. So the other auxiliary choice that you need is a character eta of E cross, a finite order character. And so at the end of the day, what you get is a triple product that involves your original form, which I'll call FB, the theta function associated to eta, and then this form GB. Okay, and the way the weights work out is this has parallel weight 2, this is parallel weight 1, and this is parallel weight 3. Okay? And so the main point is to choose the G and the eta in such a way that this triple product integral is non-zero. And this is pretty easy to do because the only fixed thing is F. The other two things are varying, so you just have to sort of squeezing this weight 2 form between a weight 1 and a weight 3 form. Okay? So the non-vanishing of periods comes from the theory of the triple product. Okay, so then we need to show that this psi 0 is a Hodge class. And this is kind of hard, and for this we use a hammer, we use the actual classification of automorphic representations. So we use the classification of automorphic representations on this group in terms of local and global A packets. Okay. And the basic idea is that whatever this automorphic representation, if you look at the corresponding local A packet at infinity, you can look at what the representations are and what degrees of cohomology they contribute to. And in using this, what you can show is that if you take the DD part of X and take the pi isotopic component, this is essentially everything in H2D. That's sort of the main point. So if we take the pi isotopic component of all of H2D, it exactly contains just DD classes. And so, but of course this guy contains H2D of XQ pi, and that's a sub-Hodge structure. So what this tells you is, okay, you've constructed something over here, but you can take some, you can modify it such that in fact it lands over there. Okay? And then it's a Hodge class. It's a rational Hodge class, so it's a rational DD class, it's in fact a Hodge class. So that's that, and then finally the last step is to understand what the Galois action on this H2D is, and you want to prove that that's state. Okay? All right, so that's a sort of brief summary of the first theorem. The first theorem was just that this is represented by a Hodge-Tate cycle. Okay? All right, now I want to say how we upgrade this to this notion of motivated cycles. Andre, what time am I going till? I forget. You started at 10, right? Or till the hour? Yeah, till the hour. Okay, great. Okay, so so if you want to produce a motivated cycle, then you really need to produce a cycle to start with, because after all, motivated cycles come from algebraic cycles up to inverting left sheds, right? Now, and the problem is that on this U22, or this product of U22s, there aren't cycles in the dimension that you want, okay? But you can do the following. So we have U22, U11 cross U11, and inside U22, you can look at U21 or U21 cross U1. And in this picture where U22 corresponds to O42, it turns out that, so inside here you have O22 cross O2, and this U21 also corresponds to a U21 inside O42. And the idea is that, okay, we've constructed a class over here, right, which we'd like to prove is motivated. We'd like to prove it somehow comes from an algebraic cycle in some way. So what we do is we have this X, and we have X1 cross X2. We look at embedded groups of this sort, right, and this allows us to construct a sub-Shimura variety, which I'll call Y. Okay, and properly speaking, I mean, of course, we have to do everything with inner forms. So it turns out that you can do this. I don't want to get into the linear algebra involved. But the point is that there is a Y in X, and we prove sort of two theorems. So theorem 1 is the following. So remember that we have this class C0 over here. Theorem 1 is the following. Says that, and let's call this map I. So this says that C0, let me write it this way. So there exists a Hecke operator T on X and a DD class on Y, which I'll call C on Y, such that, okay, let's look at the numerology of this for a second, okay? These varieties both have dimension D. So this is dimension 2D, this variety has dimension 4D. So the dimension is 4D. This variety has half the dimension, so this has dimension 2D. So the codimension is 2D. So if you start with a DD class over here, right, and push it forward, then this DD class will give you a class that is of type 3D, 3D up there. Okay, so in this set, so you have something that's of type DD over here. When you push it forward to X, you get something of type 3D, 3D. But now we invert left sheds. So if you invert left sheds, then so left sheds, L to the 2D, will take DD classes upstairs to 3D, 3D classes. So now you invert left sheds and then apply this Hecker operator, T star. All right, so the theorem is going to be that there exists a Hecker operator T and a DD class on this Y, such that when you do this thing, you get some scalar multiple of your C0 where C is not 0. Right. So that's the first theorem. And the second theorem is that, in fact, this class C on Y is the class of an algebraic cycle. And not just any algebraic cycle. Again, this is related to Kudla-Milson theory. Inside U21, I mean, you have a group which is a product of U21s. You have U21 to the D cross U3 to the N minus D. And you want to produce a class of type DD. In other words, you want to produce a cycle which is of codimension D. And there are obvious cycles of codimension D that come from embedded U11s. So it comes from embedded U11s inside. Okay, so C is the class of an algebraic cycle, and in fact, coming from an embedded Shimura variety on Y. Okay. So I don't have time to explain the proofs of these, but I can, if people are interested, I can sort of explain this later. But so I just want to say that we sort of hope that this picture generalizes. So the simplest case you can think of. So by the way, this completes the proof. I mean, these two theorems together imply the fact that you get a motivated cycle. So let me just say quickly how you might expect to generalize this. So think about the following case. Say I have two groups, G1 and G2, with unitary groups, U of W1, W2, and let's say X1 and X2 are the corresponding varieties, and let's assume that, let's say G1R is G2R, which is UPQ. Okay? Then you can do exactly the same thing we've been doing, which is you can take UW1 cross UW2 and embed it inside the direct sum. And what this corresponds to, the infinite place, is UPQ cross UPQ embedded inside U2P2Q. And what this suggests is that inside this U2P2Q, you can look at other auxiliary UPQs. So other groups that look like that. And what we sort of expect is the same sort of, this is like a meta conjecture if you wish, or we expect that you can realize functoriality in this way. Namely, you start by expect that there exists some linear combination called delta of embedded UPQs such that, and a Hecke operator T on this big X. So again, you have X1 cross X2 into X, such that if I do the same thing, which is I take I think of delta. So delta is gives me some cohomology class upstairs. I take the class of delta, and then I invert left sheds. And you have to apply, I think it's minus 2PQ, equal to the 2PQ inverse of delta, and then apply this Hecke operator T star, and then restrict to X1 cross X2. This is a motivated cycle that realizes functoriality. Of course, you have to do this one automorphic representation at a time. So, say for a fixed tempered representation. Okay, so this is a nice picture because it tells you that functoriality is really given by something fairly geometric. But what I like about this is that these general conjectures just tell you there should be an algebraic cycle, but nothing about what that cycle should be. And it's not okay. Even if you proved it, it's not clear it would be particularly useful arithmetically. But this is much more explicit. This is saying that there really should be a motivated cycle that you can construct in a fairly explicit fashion that realizes functoriality in these cases. And it would be nice to generalize this further, but this is sort of what I mean. We can't prove this also. The headache really is exactly proving the non-vanishing of periods. And the point is that in the cases that we looked at, we use these exceptional isomorphisms and so on, and we have some explicit construction of this cohomology class using theta lifting, and then we can use the seesaw to analyze the period. And in general, you can sort of stare at the classification of representations, and you can stare at these A packets and so forth, and you can see there are these representations that you expect that will help you out, that should work, but then you don't know how to construct these by using theta lifting. So we don't, we have no method to prove the non-vanishing of periods. It's also outside the realm of the usual GGP formalism because you're thinking of UPQ cross UPQ inside U2P2Q, and nobody seems to know how to handle that. Okay, let's start.
Questions or comments?
Yes, the main theorem holds for local systems as well. Yeah, yeah. So all local systems, all cohomological forms, right? Yeah. No, because see, their paper sort of does the opposite thing. So in their paper, they have lots of explicit cycles, right? And then they show that these cycles fill out all the Hodge classes. That's what they show. They're proving the Hodge conjecture in some range. We are doing the opposite. There are no explicit cycles, but we're producing a Hodge class. So it's sort of the opposite.
What questions or comments? Let's thank Kartik again.